Hey everyone, my name is Lyndon Hillenbrand. I'm a Cloudera employee, and today we're coming to you from Cloudera HQ. We're going to talk about an introduction to Pig, what Pig entails, an overview, as well as how it's being applied today, and how you can use it in your Hadoop environment. So what is Pig? Where's the motivation behind it? How is it being used? Where was it created? We're going to go through the data model and architecture, some of the components, and then I'll show you Pig Latin by example. So what is Pig? Apache Pig is a platform for analyzing large data sets. Pig's language, Pig Latin, is a simple query algebra that lets you express data transformations on large data sets on your Hadoop cluster. It is not a declarative language like SQL, but a data flow language. So what are Pig's benefits? It's a simple to understand data flow language for analysis. It's a fast, iterative language with strong MapReduce compilation engine. And its rich, multi-value nested operations allow you to perform strong function on large data sets. So where is the motivation behind Pig? Really MapReduce requires a Java programmer. So the solution was to create a system where users are familiar with scripting languages, like Python, like Ruby, or PHP. And as we go through today, I'll show you a lot of examples where Pig is very familiar to something like Python. Now, MapReduce can require multiple stages to come to a solution. And as an example, in one Pig test, we wrote 10 lines of Pig Latin, which compiled to 200 lines of Java. What took 4 hours in Java took 15 minutes to write in Pig Latin. It's a phenomenal improvement. A user has to reinvent common functionality, like joins, filter, etc. in MapReduce. Pig provides common operations, like join, filter, and sort, for these types of problems. MapReduce has a long development cycle with rigorous stages. Pig provides fast iterations, provides productivity gains. And the programmer can leverage things such as nested types to do powerful equations and aggregations. So how is Pig being used today? Well, there's rapid prototyping of algorithms for large data sets. There's data processing for web search platforms, ad hoc queries across large data sets, and weblog processing. And as a performance benchmark, currently it's about 1.1 times the standard MapReduce speed. This was done on something called PigMix 2 by Yahoo Research in March 2010. And you can find that at the wiki link on apache.org. So how do you access Pig? You can access it through something called Grunt, which is a Pig shell. You can submit a script directly. You can run a Pig server Java class, which is like a JDBC interface. Or you can use Pigpen, which is an Eclipse plugin. So the components. So Pig resides on the user machine just like Hive. Your job is submitted to the cluster and executed on the cluster. And it compiles down to several MapReduce jobs, all on extraction from the actual user interface. There's no need to install anything extra on the cluster. So it's just as simple as this diagram. So how does Pig work? Let's take a count job as an example in Pig Latin. What you need to do here, as you're evaluating Pig Latin, is take everything line by line. Right? It's a data flow language where each one is executed by itself. So A, B, C, and D are executed alone. Once you submit this job, on your Hadoop cluster it'll parse, check, optimize, and plan the execution of your job. User doesn't have to worry about any of that. So what are some of the data types? Well, it takes the native Java data types as integers, long, floats, and doubles. These will act the exact same way they do in Java. In addition, Pig has a char array and byte array as values. It also has complex types, very similar to Hive. It has a map, a tuple, and a bag. Now, the similarity in Python is where it comes in tuples and bags. For you scripting folks out there, tuple is an ordered list of data, elements that may be of any scalar or complex type. And a bag is an unordered collection of tuples. So you can have multiple bags within a tuple, or multiple tuples within a bag. So first, how do you load data? Well, the Pig data loader is extremely smart. You have Pig storage, bin storage, binary, text, or even Pig dump. So you can store data as field delimited, you can store it as binary, you can store it as sequence, plain text, or even a string representation of the data. So let's start with an example. Let's find some excite logs. If you have the Cloudera VM, you can go to user, share, doc, Hadoop Pig, examples, and then data. And there's a screen capture on the slides. Then we need to start the Pig shell. So to start a terminal, type pig-x local. You'll see a grunt prompt. When we specify local, that means you're running in standalone mode. Pig has two modes, standalone or distributed. Distributed being that when you submit your job, it runs on the cluster. So to do an aggregation, let's count the number of times each user appears in the Excite dataset. Very simply, your log, which is an alias, gets load, and then your file. Now the file becomes log in the Pig script. You specify your data types as well as your variables. Now if you notice here, user, timestamp, and query are different variables or columns, and we're not specifying any data type with them. Very similar to Python. Then you group, count, and store. And we can see the results below. Now let's take a closer look at exactly what's happening in the script, because we see several functions: load, group, for each, generate, count, and store. So data sets and aliases. Each statement defines a new data set. Each data set is immutable, and data sets can be given aliases to use later, just like variable names. So in this example, we're loading excited-small.log as several variables, user, timestamp, and query, and the alias log is expecting that data in those three columns, or variable types. So load returns a tuple. So when a tuple is a relation, right? Each tuple has multiple elements, can be referenced by position or by name. If you're not setting the data type, you must refer to your relation by basically reference. So $0, $1, just as Python or PHP, that's how you refer to these variables if you haven't declared them. Then we have bags and for each. The for each and generate statement iterates over members of a bag. So in this case, we're iterating over for each log, or bag in the log, generate a user and store that in user names. So the result of for each is another bag. Elements are named as the input bag. So positional reference. So I started talking about that before. And what that means is a perfect example here. Just as a username statement we just looked at, you can say for each log generate $0. This looks at the elements in the first part of the log and assigns that to username. And pig grouping is a separate operation from applying aggregate functions. In the earlier example, the output of the group statement is a key and a bag, where key is a group key and bag contains a tuple for every record with that key. You can see the example below with Alan and Bob, where Alan is looking at a bag of tuples and Bob is a single tuple within a bag itself. Then we look at grouping and types. So group by makes an output bag containing tuples, which contains more bags. Quite simply, you can group bags into other bags and tuples into bags. So the in, if you look at bag of, is user, query, and time. The out is a bag of grouped, bag of user, query, and time. It's just an abstraction of the original bag. So let's apply a filter to groups that we only want. So basically, you can use a filter function as basically a non-join. So we have the filter statement midway down, and what we're going to do is filter out the count that's greater than 50. So let's say, as another example, you wanted to filter out null values. You could say filter out is null. It's a perfect data quality example using Pig. So let's sort the high frequency of users by frequency. So basically, you can say sorted equals order filtered by count. Right? This will give you a sorted order of users filtered by their count. Just as a stop point here, if you're getting confused, you can use the illustrate command to understand what we've defined as our schema within our bags, tuples, or aliases. And you can see a sample of derived results. All you need to type is illustrate and give it the alias. You can also perform multi-query execution in Pig, and that's done through dump and store. So dump will actually push the results to standard out. That executes immediately on the command line and in the script when you run it. Store will parse the entire script, and prior to writing for efficiency purposes, wait till you're done evaluating the entire script and store that into the Pig format. So in A, we're loading a certain input file. B and C operate on A. Now in older versions of Pig, B and C would have been two separate MapReduce jobs. Pig's gotten smarter. It will now wait, and it will use store, and it will run one MapReduce job with two outputs for efficiency on your cluster. So let's prepare data for a join. Right? Running a Pig job to prepare the Shakespeare and King James Bible following the example. So we're going to use things like tokenize, filter, group, and for each. We need to flatten the set. So tokenize is an operator that returns a new bag for each input. So you have A, you have line 2, line 3. After tokenize, you now have line 1, word 1, line 1, word 2, basically a key value system. Then we're going to operate our joins. Let's use a join to find words that are in both the King James Version of the Bible and Shakespeare's collected works. So we'll use a load function for both files. Then we'll say in both, let's join by word KJV. Then we're going to store that in an in both into our output file. Very simple, very powerful. So beyond joins, we have anti-joins. I talked a little bit about this before. And you have things such as filter. And what this allows you to do is find words that are not in your input data set. In this example, we're going to find words that are in the Bible that are not in Shakespeare. And you can think of multiple examples where to use anti-joins. You can look at nulls, you can look at bad records, any other type of data types you want to filter out. So just another note on anti-joins, a lot of people, when they look at large data sets, don't think of all the misrepresentations of data they might have in there. If you look at 10 terabytes of data, even 1% of that is a large number of records that could be bad. So data quality and filtering out nulls, bad records is extremely important, and Pig can help you do that. So co-grouping. Co-grouping is a generalization of grouping where keys for 2 or more inputs are collected. It's very powerful, and we can take an example as looking at the output of the group statement in the previous slide. So using types. By default, Pig treats data as untyped. You can declare types at data load time. So we can say, in this example, the frequency will be an integer, and the word will be a char array. If the data type is not declared, just as Python, the script treats the value as a certain type. And Pig will assume the value of that certain type and cast it. So if you send in a number and you haven't declared it, it'll cast as an integer. It may cast it as a string. And Pig will decide that on load time. So let's take a look at custom loading and share. By default, Pig assumes data is tab separate UTF-8, and the user can specify a specific delimiter. You can even write a custom load function, such as pig JSON loader below, to load JSON files into Pig. Pig is very flexible, and that's where the power comes in. You can write multiple UDFs, custom load functions, all in Java that you can use within Pig. Pig provides 2 statements in order to use UDFs within Pig, register and define. So register actually registers a jar file in Pig runtime, and define creates an alias for the UDF or streaming script. These can be used to do column transformation, filtering, ordering, or custom aggregation. So before you run off and write your own Pig UDF, you can take a look at the Piggy Bank, which is on the Pig Wiki, where people submit open source contribution UDFs. You may even want to do that yourself. So Pig is very strong because it also supports nested operations. People are familiar with nested operations from Java, from Python, Ruby, or PHP. A for each statement can apply a separate operator to every tuple in its turn. Let's say you're using multiple tuples, or multiple tuples nested within each other. These for each statement can also do that, just as an if-else, just as a do-while loop within Java. So using the previous session's analysis example, we can assume the UDF requires input to be stored by time. We take a look at splits as well. Data flow need not be linear. A split can be used explicitly to split what time the data is coming in at, or what the data is being grouped by. So finally, let's wrap with a Pig cheat sheet. So you can use multiple of these commands, functions, or operations in your Pig script. You can also find all the Pig functions at apache.org. So Pig is an official open source project under the Apache 2.0 license. It's an official subproject of Apache Hadoop. It can be found at pig.apache.org. And the current version is 0.8.1. It was released in April 2011. Thank you very much for your time today. That's Introduction to Pig.